Hey everyone, I'm Mauricio, and this is Sylvia. A little bit about us. Currently, we're both members of technical staff at Eve. Previously, I was a senior machine learning engineer at LinkedIn, undergrad and master's from Stanford in computer science. And Sylvia.
Hi everyone. So yeah, I'm also a member of technical staff at Eve. Previously, I was a full stack engineer at Blend, and before that, a UI engineer at LiveRamp, and I went to the University of Waterloo in Toronto. All right. Well, before we begin, I have a question for everyone. Have you seen Anne Fong? Yes? Okay. I imagine many of you have seen the sign or one like it while driving down the freeway, but maybe not as many of you know what Enfong is. So Enfong is a plaintiff firm. Does anyone know what a plaintiff firm is? Don't be shy, put your hands up. No? Okay, well, plaintiff firms fight for justice for their clients, the Davids against the Goliaths. As you can see, poor Anne Fong on the left here, and her team of maybe 5 people is fighting against these super large corporations with multiple times more resources than her. And as you can imagine, this is very, Anne Fong needs some help. So enter Eve. What Eve does is Eve levels a playing field for plaintiff firms like Anne Fong. We work the entire case with our customers from intake all the way to litigation. And in order to do that, first we ingest hundreds to thousands of documents and call transcripts. And we use that as context in features like drafting, case intelligence, and intake, and most importantly, our most powerful and most used feature, chat, which Mauricio will talk about.
So over the course of the next couple minutes, I'll be chatting about what we previously had, what the problems were and how we fixed and have improved chat. So to start off, we'll talk about what we previously had, our non-agentic chat. So you can imagine lawyers are coming to the product and they have questions about their case, right? Maybe there's an accident, a car accident, insurance is not giving the client enough money, they're in debt, they're in medical bills, and the lawyer's helping them. So question like, how many times did John visit Dr. Doe? We'll run retrieval over it, so embedding-based retrieval, BM25 retrieval over all the documents, our case intelligence, which is like our pre-processed documents, our CRM data, and use LLMs plus these indices to do the retrieval. And then we'll hand it over to an LLM with the right information to output the results, of course with like good citations, making sure that lawyers can always click back and understand exactly where we got the information from. So one thing that we noticed when we ramped this out to our hundreds and hundreds of law firms using our product was that sometimes we would run into issues around retrieval. So documents are not found, there's missing information, not sufficiently exhaustive. And this is critical for law and something that we set out to improve based on the data. So how we worked on this problem was first, there's a couple key components. One, sometimes lawyers will ask questions like, hey, summarize this case. And it's not always clear, if you just look for embeddings that are similar to summarize this case, you embed the question, you run embedding-based retrieval, or you look to BM25 keyword, see where summarize is contained in the documents. That won't necessarily give you the best answers. So what you want is often to do some query planning, figure out, okay, given this question, what are the things you want to look for in the documents? So that's the first component the agent is doing now, and that's been a big differentiator. Second one is iterative retrieval. So often some of these harder questions will require first you need to find one thing, then you need to find in order based on that piece of information, you need to look for the next thing. For example, someone might ask, okay, well based on this specific medical condition, what were the visits? And so first you need to find the medical condition, understand it, and then only then you can figure out the right documents that you need to look for and use to answer. So here's a little demo of the agent. So someone says, can you provide a quick summary? The agent is thinking. The lawyers can see the thinking choices if they'd like. Optionally, we review the matter documents. This is a relatively simple run. And then we process the final output. So you can see the agent is thinking through it and outputting the final results in a detailed damages summary of what happened with clickable citations to understand exactly, lawyers can verify and understand exactly what happened. So, oh, so beyond all of these components, we have a couple of tools. Next slide. Okay. A couple of tools that are used to do this that the agent uses in order to answer the question appropriately. You can think of a lot of these tools as like the same. And you can think of our product, this agent, as almost like Cursor for lawyers or Claude Code for lawyers that needs to be able to understand the context and be able to answer these questions appropriately. So tools to be able to find the appropriate files that they're mentioning if they mention a file, be able to read files, search within files, retrieve a lot of our access to information like CRM data, case intelligence, which is our pre-processed knowledge graph of sorts, and be able to run all of these tools in order to best answer this query. So this fulfills, via these tools, being able to do query planning, right? The agent, when it's looking for information, it's able to tell the queries of what it wants to look for. It's able to do iterative retrieval based on the results, reason, and move forward. And all comes together in order to provide a really good experience for these lawyers. So far, we have found that, the lawyers have been loving it. Crushes good at difficult questions. And so far, we've been able to help our end users, those lawyers who are then helping these plaintiffs through personal injury and labor and employment and other fields. So with that, I will hand it over to Sylvia to talk a little bit more about Eve. Just before that, I will add that, I think our vision for this agent is currently we have a ton of different workflows over the course of our project. There's a special workflow for drafting. There's a special workflow for inline editing. All of these separate LLM-backed workflows. And one vision for this agent as well is to be able to be cohesive with all access to tools, access deep knowledge about the product and the domain to be able to unify everything. So be able to put it all together into one cohesive experience so that lawyers feel like they're interacting with a coworker, a really smart attorney that can help them answer their case. And so all of that is our vision of what's coming next.
Thanks, Mauricio. So it's a very exciting time to join Eve. So far this year, we've had over 400% team growth, 800% customer growth, and 500% revenue growth. And we raised a total of $61 million from top firms. And just between us, we're also one of the top performing A16Z firms. So if you're looking for a high growth startup to join with very talented engineers, you can find Mauricio, myself, or Jeff after this presentation. And we'll pass it over, I guess, if anyone has any questions. Oh, sorry. The slides.
Question? Which vector database do we use? So we use TurboPuffer as our system.
You mentioned a knowledge graph for case studies. How's that represented? How do you plug in LLM, or how does the LLM?
Yeah, so we have a part of our product that's case intelligence, as I mentioned earlier, that is a knowledge graph of sorts. So what that does is it pre-processes a lot of information that's useful for attorneys to be able to understand their case. One of those key components is a ledger, which is a separate. So attorneys often want to know, hey, what were all the costs of all the medical treatment that someone got? And so be able to break that down of hey, these were all the visits to the providers. These were the total costs. This is the total cost across the case. We also have information around, all the visits to the doctors, any bad facts, any positive facts. And so all of this is, interactive. Attorneys are able to see almost this case overview of sorts of what the case is. And that's really useful for the LLM as well. When at this point it can just retrieve it with the agent, retrieve when it's relevant in order to get some good background information on the query. You can think of this almost like Claude MD of sorts, but much more thorough, where it's some pre-processed information on the case that helps the agent be able to carry out its job appropriately. Question? Yeah, that's a great. So the question here is, do we have another agent to be able to rank which cases are good and which cases are bad? As you can imagine, these plaintiff firms have very high volume. there's a lot of accidents, there's a lot of people that are like medical issues or fired, etc., labor and employment, people that need access to legal care. And so how do we deal on like the process at the beginning, like, oh, should we rank someone to take on a case or not take on a case? And we have a separate product for that, so it's like an intake product, which is actually now doing a voice AI. I'd like to be able to take on after hours calls. So someone calls, at 2 a.m. and like be able to answer the call and be able to get some information from them, be able to do transcripts of calls when someone calls, and then processes all that, like gets really good information for attorneys, ranks that, and then they can see that in the morning or whenever to be able to decide if they want to take on a case or not take on a case. Question?
When doing retrieval on, let's say, legal documents, there are like several bullet points usually that like refer to some other document or some other bullet point by number and not by like a particular word. So how does that work in like retrieval? Because from what I understand, it's usually like by letting word embedding of a word or something. So do you need to do anything special for that?
Yeah, so the question here is how do we deal with document references? So say one document is referring to 5 other documents and you're able to read it and then based on that look at other documents. The answer there is that's where retrieval, like an iterative retrieval that we talked about, an agent where it's able to read something then act on it is super, super useful. So you can imagine it reads a single document which might contain some medical records. They see that, oh, these medical records are referencing other visits that are useful, and then is able to, based on that, then look at the other medical records and so on and so forth until it has the nice, all the information it needs in order to answer the question accurately. One more question?
Do these agents pull database from, let's say, the doctor's hospital, or doctor's hospital, or do the plaintiffs have to manually input the names?
Yeah, so the question is, how do we get access to all of these documents? Are people manually uploading it, or is there some other system? And the answer there is we have integrations with all the major document management systems and CRMs that plaintiff lawyers are using. So there's like OneDrive, there's Clio, there's all these other ones that are like like Clio specifically is very common for the legal industry. And so we integrate with all of that and sync it automatically. So that every time they have a new case, it's all pulled into Eve. Any new documents are pulled into Eve, and then we're able to use the AI appropriately to answer their questions. One more question?
I assume hallucinating for this model is going to be more expensive, mainly because of the domain of this company. So do you penalize the scoring system doesn't penalize hallucinating a lot more than a regular model, or how do you prevent that from happening?
So is your question around how do we prevent hallucinations? So it's a great question. Like, what do we do about hallucinations? I think there's a couple key components here. First is like very careful evals, making sure to optimize the system in order to reduce hallucinations. So there's a lot of different techniques that you can read about online. I'd be happy to send you some links on ways to minimize hallucinations with the models. One like really simple trick is you can just tell the model like, say I don't know if you don't know. You can do a lot of those like different components in order to make sure to minimize hallucinations. Of course, like feeding it the right information is also critical in order so that it can operate on it, and also using the state-of-the-art models as well. And then on top of that, there's also systems of verification that we do on top of the output. So verifying all quotes and showing the users if we can't verify those quotes. Giving citations to the data so they can click on it and see exactly what section of the page we got this information from. All of these components are critical, like multiple layers of defense, in order to make sure that hallucinations are minimized or eliminated.
For next 10 minutes, we'll talk about how to run models on device and how to enable on-device AI use cases on Snapdragon platform and on different Android devices, for example, and almost, let's say, auto or IoT devices as well. So first of all, let's understand, right? Every day we are surrounded with all types of use cases, like for example, from dictation to video calls to taking photograph. All of these use cases are powered by AI. And it's important to see all of these use cases can be enabled with cloud as well. Like you might ask, okay, it's very easy to train a model on cloud. Why not just do inference on cloud? But if you consider some other factors, for example, cost, let's take an example of ChatGPT. The ChatGPT inference cost are way more than its training cost. And same applies for small models as well. So if you run a model on device, developer is paying zero. And we all are carrying like very powerful devices in with us. So running models on device makes total sense from a developer's point of view. Because as you scale, your cost is staying constant, that is zero. Second and most important is privacy. If you run a model on device, your data is never leaving a device. And when you are, like, as a developer, when you're building something, we have to think from a privacy perspective of customers. And privacy becomes like a very crucial aspect when you develop apps. And third is performance. If you're running something on device, there is no network coverage, right? And you're not sending any data over the network, no images, no videos. So your model performance will be at par, and it will be like the best performance that you can get on the device. And some of the use cases, for example, camera, you cannot run on cloud. You can't take a, like, let's say, video as and doing a segmentation at the same time if you're doing it on the cloud. So all of these use cases make sure that on-device AI is actually important. So we looked into what are the challenges that developers are facing as they deploy their models on device. And you can see, like, these are like one of the like top 6 categories that you will see one of the error going into. So we looked over all these issues and we categorized them into 3 problems that we can actually solve that will help most of the developers. And these 3 categories, getting started, that means how do I find the right model for my use case? If I have a right model, how do I convert to a model, a deployable platform that I'm targeting to? And let's say if I have solved that problem, how do I rapidly iterate over the model use case to make sure I have a best performance and I have best accuracy that I'm looking for? And even if, let's say, I have that, how do I scale to multiple devices? Because I'm not going to deploy a model only on, for example, latest and greatest device. I want to deploy the same model on a variety of auto devices. I want to deploy the same model on a variety of different IoT as well as mobile devices. So how do I basically make sure my model is performant everywhere? So these 3 problems, to solve these problems, we came up with something called Qualcomm AI Hub. It's been like more than a year we launched, and more than 2,200 companies are using as of now. We have collaborated with different collaborators, for example, AWS, where you can train your model with Amazon SageMaker and then deploy with Qualcomm AI Hub. We also work with very closely with model makers, for example, Meta, Microsoft, to make sure all the LLMs are available to you on day 1 for on-device use cases. Like if you check Qualcomm AI Hub today, you will have most of the large language models available to deploy on the model on device. So Qualcomm AI Hub has 3 offerings. You can download a model that is pre-optimized. So we have something called Qualcomm AI Hub models, which has pre-optimized, pre-quantized models for a variety of different platforms to pick up from. Let's say your use case is not covered in Qualcomm AI Hub models. Then you can bring your own model and then use AI Hub platform to compile, quantize model yourself and then deploy on a platform of your choice. And it doesn't stop there, because if you compile a model, you do want to deploy it somewhere and you need some guidance. So we also have something called AI Hub apps, which will help you see how the model actually works on your device. So the Qualcomm AI Hub models that we just talked about, that has like more than 175 pre-optimized model. We release every 2 weeks. We have like very rapid iteration. And you can pick up a model right from here. You can download TF-Lite model or QNN context binary and get going. Let's look into developer workflow. We'll go over this like very fast since we have a very limited time here. So high level, you pick up a model on the left, and then you pick up a target platform. For example, you pick up, let's say, auto devices or a mobile device. Then you pick up a runtime, let's say TF-Lite, because you want to target on most of the Android devices. And then you can rapidly iterate where you do performance evaluation, you do accuracy evaluation, and once you're happy, you go and deploy the model. And you can start with model from Hugging Face. You can bring your own model. You can pick up a model from AI Hub models, modify, you can train it, you can fine tune it, and then you can use the same use case. To compile the model, it's just like 6 lines of code where you use like Python API. You submit your torch model, you select a target device and a target runtime. For example, here we are compiling torch model into Onyx. Once you have compiled model, you can do Onyx to Onyx graph transformations, or you can also quantize your model. To quantize this model, you use Hub Quantize Service, which is powered by AMate tool, which is a quantization open source tool from Qualcomm. Here you can provide your own calibration data, so you know the quantization is basically capable using your own data. Once you have quantized your model, you can compile that again. And for example, it's in this case, you compile it to TF-Lite model. And now, just compiling the model, you have no insights. So that's where we introduce something called inference job, where you run a model on a real device. So we have a device farm that we use, where your model will be running on an actual device, and then the data will be sent back to you. Now the beauty of this is you can build so many things around it, because now you can build your own evaluation pipeline to make sure, for example, let's say if you're building an object detection pipeline, you can have an MAP-based pipeline here, where you can evaluate that your model is actually doing what it is supposed to do. And once you're happy with the performance of the model, then you go and check how your model performs, and does it meet your, let's say, target. For example, if you plan to do 30 FPS, does our model do that job? That's why you can use profile job to see the real-time performance of the model. We don't have time, so I couldn't actually show you like how the profile job and inference job does look, but it also gives you nice visualization where you can see the hotspot and you can find where your model is not performing well. To like that kind of gives you an insight where you can go back and modify your model in PyTorch and connect the back. So it makes it's very easy to iterate rapidly on your model pipeline. So basically, to summarize like what we just talked so far, Qualcomm AI Hub is basically bring any model, any framework, any runtime, and any operating system. And you can do it in 5 minutes, in less than 5 minutes of code. We have a very active developer community. I would highly encourage you to join the community. If you have any questions related to maybe on-device AI or model conversion, we are very active and we'll be happy to help you out. I'll wait for some time for you guys to take photo. Yeah. Okay. We have very useful resources that are like more than useful than Qualcomm AI Hub as well. You can learn about quantization. You can learn about different compilation and optimization techniques as well. These are some of the apps that have been shipping and that have used AI Hub to build their apps and optimize their AI models. I have prepared a small notebook for you guys to try out, where basically we start with Torch and compile, quantize, and go all the way to TF-Lite. So the APIs that I showed you, you will have them in a notebook, and you can just write down yourself. I always thought, I think having some demo that you can run is actually more valuable than me showing something. So, yeah. We also have sample apps. I'm just sharing links if you need. I think, yeah, that's all from me. If any questions, I would be happy to take it. Cool. No questions. Thanks. Okay.
What's your favorite feature?
About AI Hub? Yeah. So, quantization job, because I work on quantization recently, because I think quantization is really helping us enable many different use cases, specifically LLM, right? You can't run a model without quantization on device. And that's something I've been like heavily working from last couple of months. And I think second is basically the ecosystem, because it allows you to run anything like super fast, right? So before Qualcomm AI Hub, it was very difficult to run something because developer toolchain is built very differently. So if you have something that is like taking care of that automatically, it works amazingly. Like I think instead of me, I can quote something like from one of our customers, figuring out the whole pipeline and understanding why something is not working at TF-Lite because the channel layout is different, right? Like it's bizarre. Like if you don't understand like the internals of the toolchain, and we allowing that seamlessly, and how that integrated like nicely is something that is helping many developers. So I think I would say integration first and then quantize job. Yeah. Yes, please. What type of quantization is? That's a great question, actually. So, I would say quantization is kind of a metric, right? Like it's like a parameter where, let's say, on the left-hand side, you have fully quantized model. Let's say if hardware supports int8, you can go all the way to int8. But now you're saying no to accuracy. So it's like a fine balance between like your application. So it depends on case-to-case basis on what model you're working with. Qualcomm does support int4 quantization as well, and we are actually going even more in detail. I think like the upcoming release like that is going on in Snapdragon Summit. You will find out more about what is coming up on the new architecture. But in hindsight, for LLMs, we usually go for W4 A16. Basically, weights are W4 and weights are int16. And some of the layers are int8. That is the typical use case for like LLMs. But for most of the other use cases, int8 works like fine. So we recently introduced something called light MP, where you do 90% of the model in int8 and you do 10% of the layers in int16. Because in the model, you will always find there are some layers, those are very sensitive, and most of the model can just run fine. Like for example, let's say if you have an object detection pipeline, you might have something called mask, and that might throw it off. So let's say just making that in 16 might do the trick. Cool. If you still have any questions, let's say that come up later, please post it on our Slack channel. I will be happy to help you out. Thank you.
Hey everyone, I'm Elvis. I don't have a QR code, but Sarah's in the back, and she's our lead recruiter. Sorry. So if any of you guys find this interesting, please talk to her. Yeah. So I work at a startup called Chalk. We recently raised a Series A, and we make Python go fast. And so Chalk was originally built for these two use cases. So primarily recommender systems, fraud detection. The two constraints here is that you want fresh features, so that's like features from a live data source, and you want them at very low latency. And the reason that this is interesting for us is because this is the same type of data workload that you have for context engineering. It's like being able to get the right data to an agent very quickly. And so people end up building either an internal solution for this because there isn't an off-the-shelf solution. And the core problem they're trying to solve is getting the right data from the right place at the right time. And so I made a quick map of some of the data solutions that are in the space. And the whole idea here is that if we can build something that covers low latency, high volume, and also complex data orchestration, then a company can go from deploying a machine learning model twice a year to like twice a day, which is a really big delta and a pretty good value prop. And then in addition to like these two constraints, people also want to be able to ship models quickly, add new data sources very easily, and also integrate unstructured data with LLMs. And so the way that this works is that we have two components. So one of them is dynamic query planning and optimized execution with Velix. And so Velix is an execution engine, and I have some slides on that later. But this is kind of like I guess a query plan. And so essentially given some user, or I guess in this case a review, we want to fetch like the feature normalized rating, and we also fetch a bunch of other features. And the idea is that Chalk can go out to all these data sources, jump across a bunch of different tables, fetch features, transform them, compute new features, and then give you back the features that you want back. And so to make this possible, it has to be declarative. So think like SQL. You tell SQL what you want, and then SQL can, under the hood, optimize it and make it fast. And so the way that we do this is that we make it really easy for a user to express their features and how they relate to each other. And then we can build a DAG from that, and then we can take a subgraph of this DAG and then build a query plan from that that tells us how to get those features from all these different data sources. And then a second point is that Chalk has to be a wide enough platform that we can push down filters and projections to the underlying data source. That way these queries are really efficient. And so this is how we make this DAG. And so I have a transaction, and you can see that user ID, instead of it being an integer, is going to point to the ID feature of another feature class. And so if I have a user, I can see that, okay, it's pointing to the ID of this user, and so now Chalk knows that this is a foreign key. And the nice thing is that we can then create an abstract, I guess, variable called transactions, which is a has-many relationship to transaction. So I can say that this user has a bunch of transactions, which are a data frame, And then we can run projections against this transaction. So like this. So I can say project the total column and then take an aggregation, and then that can be a new feature. And then we can also have these accelerated functions that run in C++. So this max by will run in C++ instead of Python. So Python for us is a user interface to make it easy for people to express features and what they mean. Okay, cool. And then we have this concept called resolvers. Let me jump to the next slide. And so I can have a feature, for example. So if you look at the bottom of this function, we have a user discount percentage. And if you look at this function, the inputs of this function are going to have also weird type hints. So instead of total spend being like an int, it's also going to point to other features. And so because we can make these resolvers, we can essentially compose new features by essentially making this dependency graph, right? So I know discount percentage depends on these like 6 features from other classes or whatever. Okay, cool. So that's how we build the DAG, which we then take the subgraph of. And then the way that we make this fast, and the reason that we want it to be fast is so that we can make this low latency. And this is kind of like motivating us using Python as the UI for interacting with Chalk. But we essentially want to use this thing called Velix, that way we can skip the GIL, and also so we can get SIMD, and then have like really, really accelerated computations. And so this is Velix. It's a project from Facebook. They started in like 2020, and they built it to replace Presto's backend. And I think it saves them like 100 million in compute a year or something. So it's like extremely optimized and really, really good for offline queries. And so an offline query is going to be like, think like you give it a SQL statement, and then you want to run an expression against millions and millions of rows. And the interesting thing is that online workloads are very different. So usually in an online workload, when you have like a recommendation, you're getting like one row from a bunch of tables. So that's very different than getting millions of rows from one table. And so the idea here is that if we use Velix and we fork it, and then we build a separate code path for an online workload, you can essentially unify your execution engine and use the same system for all of your data needs, right? And this is super helpful because then a company can have a single source of truth for how features are computed. So like if I compute a credit score one way, another team can use the same computation for how they want to compute a credit score. And if you standardize this across the company, it makes it really easy to build new models very fast. Yeah, and so then we can use the same query planner, same resolvers, and the same compute engine. And then you can deploy things much faster. Cool. And so one thing I wanted to point out here is that we have 2 Redis online store lookups. And so look at this expression sentiment. So this is actually an LLM call. And the nice thing is that because we control making this query plan, we can essentially save the inputs of a feature and say, oh, if I see these same inputs again, I don't actually have to recompute that. I can actually go to Redis and hit something that's been computed before. So this is super helpful when you're calling APIs or microservices that are either slow or expensive. And then the second thing is that this normalized rating is going to be, actually no. So this username, get marketplace username. So this is a function, for example, that's taking in, this is kind of hard to read, sorry about that. But this is like a function that says like, hey, we have this email address, we want to split it by the @ sign and take the username, so everything before Gmail, for example. And then if there's like a plus sign, because Gmail lets you add extra characters, we want to split that again. And so that's really easy to express in Python. And the idea is that if we can build this like transpiler that turns Python into static, composable static expressions that run natively, then people are writing Python, but nothing gets run as Python, right? So we built like kind of like this compiler that does that for us. And so everything that's yellow are Python functions that we've accelerated. And you can see that this purple function hasn't been accelerated because it's making an LLM call. And everything in Python, we just run in Ray. Cool. And then, okay, so this is my last slide. And so the key component here is that if you can make a data delivery platform that's super fast, then you can actually just compute data on the fly. And so then the code that you write to express your data models are actually your data itself. So if I have a branch of my code base, and then you make a branch of your code base, and then you change a feature, Chalk can just compute the data on the fly, and so those 2 branches represent your model. So if you want to revert your model, you just revert this DAG, right? You can just go to another git commit, and that's a different model. And then the second thing is that because we kill off ETL, because we go straight to the underlying data source, you don't have these intermediary ETL tables, we have full data lineage, because we can point to the row of the database that that feature came from. And this is super helpful because you get a ton of observability. And then the second thing is that because everything is running through Chalk, what we can do is we can actually persist every run. So think like, oh, you had a recommendation yesterday, you had like a million more recommendations tomorrow. We can save all of the inputs in Iceberg, and then we can actually rerun those inputs through a new model, which is just a branch of a code base, and then we can actually A/B test our models, which is super helpful, because then we can deploy confidence. We can deploy models with more confidence. Yeah, so that was my last slide. Cool. I know that was fast. Thank you. Yeah, so questions. And if there aren't questions, I have more slides that I can show. Yeah. 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 Okay, so the biggest benefit is that all of your features end up running through Chalk because we do the serving for you. And so you can actually, for example, put thresholds against certain features and then say like, whenever we see like this average rating or this score change past a certain threshold, get notified, which is super helpful. But the biggest thing is that most of our customers are fintech. And so they want to be able to say like, oh, someone is suing us because their loan was denied. And they can say like, we can tell you how your loan was denied because we can look at the expressions at the stag when it was denied and also look at the inputs of that. And so it makes it really easy to debug where a feature went wrong because you can trace all of the features as you have this pipeline. So those are the main two observability benefits. Yeah. No more questions.